Hello, friends, welcome. We shall start with our next section, the applications. Under this, we need to discuss about four different applications. As the first application, we will look at steel mills. What is the steel mill? What actually is the basic activity that goes on? If that is clear, then the whole thing will be clear to us. So, in the steel mill, it is the rolling of the steel that goes on. It is the rolling of steel that goes on. That is why steel mills are also called as rolling mills. Steel mills are also called as rolling mills. And what is this rolling? Rolling is the process of reduction of cross section of metal. Steel metal is there, na? That metal cross section, the geometry, we change. That process of changing, reducing that to different shapes. That process, it's a mechanical process. That process is done by rolling of the two big multiple big discs, and that is referred to as rolling of steels. Okay, so steel mill basically is a rolling mill. Okay, next, so what is the process involved here in the steel mill or the so-called rolling mill? Look at this little carefully. It is the overall process we get from the basic process. Steel in the form of ingots, big blocks, very big blocks, and these big blocks are of not much use for ordinary applications for construction purpose, etc. Hence, they need to be changed in terms of their shape. There are two paths here. You can see in the first path, the blooms, the ingots of cross section which is square cross section, they are called as blooms. The ingots of square cross section called as blooms are converted to billets, smaller size, and then they are converted to bars, rails, rods, angles, etc. And these bars, rails, rods, angles are the ones that we use now for different applications. So starting from bloom, getting these bars, rails, rods, etc., all this goes on with the basic item there being in the hot condition. That's why this line is called as hot line, or this type of rolling is called as hot rolling. In contrast, we have another path, another line, and your assumption is correct. This is the cold line. Here the metal is in the cold condition, it is not heated. And what is this? Here the ingots, the basic blocks, big blocks we get from the steel making process, they are of the rectangular cross section and they are converted to plates. They are converted then into strips, and these strips are converted to sheets, and then they are wound on a bobbin and stored. So here we have the slabs converted into plates, strips, sheets, different forms, which again are used in different applications. This whole path is not hot, it's a cold path. That's why this rolling is referred to as cold rolling. So in the overall process, we have hot rolling, we have cold rolling. So steel mills can be of two types: hot rolling steel mill, cold rolling steel mill. Now in this whole process, there are basics, differences, Can you see this? From ingots getting blooms, from ingots getting slabs. This happens in the factory workplace called as primary mill. Whereas from blooms, the application ready items, from slabs, the application ready items, all these things are done in the factories or the mills called as merchant mills. So here we have this process going on in the primary mills, this process going on in the merchant mills. That is the overall process. Steel mill or the so-called rolling mill, from ingots to the ready to use forms. Okay, we shall move on. So I mentioned that the steel mill can be hot rolled, it can be cold rolled. Again, in hot rolled, it can be of reversing type or it can be of continuous type. In cold rolled, again it can be of reversing type or it can be continuous type. Ultimately, we have four types: hot rolled reversing type, hot rolled continuous type, cold rolled reversing type, cold rolled continuous type steel mills. Four types of steel mills. First, we will take up reversing hot rolling mill. Reversing hot rolling mill. And for this, what is the input? Input is an ingot. And what is the output? We have seen in the process the blooms, the slabs. See here, input is ingot, output is blooms, slabs. And how the process is going on. So this is the whole process wherein we have ingots. Ingots are converted into blooms or slabs, and ingots are carried till this processing point on a vehicle called as car. The car will be moving on a mill bed. Mill bed is having series of rollers. On that, car will be moving, and that brings the ingot big block to this point, which is called as mill stand. It is passed through the mill stand, and output will be the bloom. And what is this mill stand? Mill stand is the arrangement of rollers like this. Can you see the solid rollers? There are two rollers here. It can be multiple rollers also to put more pressure. When we pass the metal between this space, the shape of that metal will change. It is like squeezing. You have come across this type of application? Where you have come across? Yeah, try to recollect. Rollers, squeezing. Where you have come across? Sugarcane juice making, sugarcane crushing. Exactly the same thing happens here. When you have sugarcane passed through this, it gets squeezed, the juice will come out. The application is different, but here we are pushing the ingot of larger size. When it comes out, because of that pressure, the pressing, the shape, the size will be different depending on our requirement. Now, in the first go itself, we cannot have this space too small because the whole big piece has to pass through this now. That's why this gap between the rollers is kept more, and subsequently that gap is reduced and we go on squeezing again and again. Like first we pierce, change the shape a little, then come back and then pierce, come back and then pierce, like this. It is reversing type, na? Since it is reversing type, see here, it is reversing type. We need not come back here. We can pass through this itself. So one go, reverse go, forward go, reverse go. In each go, go, in each pass, we change this spacing, this gap. This gap is referred to as stand gap. We need to have a mechanism of adjusting this gap with the help of a screw, and if the rollers are very big, with the help of the motors also. So in gods, take on a car, move on a bell bed, bring to the mill stand, pass through the stand gap, and again reverse, pass through this stand gap, reverse, pass through this stand gap. Each pass you change this gap, so that after repeated operations like this, you will have the output here in the shape of a bloom of the required size. Since the metal is hot and movement is forward reverse, this is referred to as reversing hot rolled steel mill. Okay. Next, if that is the requirement, what are the drives required there? What type of properties, features are necessary for the drive? What for we require the drive here? Mainly for moving these rolls, for moving these, rotating these rolls. Okay. So now the drives, what we require, they have to have a wide range of speed control. Not only that, the accuracy required is more. The speed accuracy required is more. Why? Because it is the speed that decides the uniformity of the pressing. Only when the pressing is uniform throughout, the cross section of the metal will be uniform throughout. The quality of the output will be better. Otherwise, it will be an uneven output. The quality will not be good. That's why the speed range has to be more and it has to be accurate. And we require frequent starts, stops, reversals. Start, forward, stop, reverse, run, stop, reverse, run, stop, reverse, run. Like this, we have multiple starts, stops and reversal. That's very important thing to be observed. Once when the process is like that, then obviously each start there will be a voltage dip, and associated with that there will be starting current which is very high, and immediately what comes to our mind? Voltage dip, a problem, supply voltage profile gets affected, starting current very high, affects the motor, it affects the grid also. Hence, there is a need to control the starting current. So, the drive requirement has to be such that the starting current is to be as less as possible. Also, the motor we use here should be very fast in responding, which means it should be with inertia which is very less, then only it becomes fast. That means when I ask it to stop here, it should stop. When I ask it to reverse, it should reverse and then stop again here. The positions, the instance at which the commands are given should be executed accordingly here. Then only we get the accurate output. So accuracy and reliability required is very high because of the positioning accuracy required there. These are all the drive requirements. Once when the drive requirements are like this, what are the drives employed there? Different types of drives are employed. First, DC motor, a very traditional motor that is employed, and that is employed with Ward-Leonard control. Ward-Leonard control you know, na? Wherein we can change the voltage across the armature as well as the flux for changing the speed. And this control comes with 4-quadrant operation, so that you can have forward reverse motoring and forward braking regenerative, reverse braking regenerative, and we have flywheel effect also included, so that the movement will be smoother, and regenerative braking is preferred because the motors used are of high capacity, and the braking regenerative nature is economical, and for very high capacity motors it's inevitable. And Traditional ward lever control is not used nowadays. Nowadays we go for thyristorized control of DC motors, and this is called as solid state ward lever system. Thyristorized DC motor control is nothing but using the converters, using the SCRs, the power electronic devices. That is the approach followed. And the other type of motors employed are induction motors. Induction motor drives are employed with variable frequency, wherein we use DC link inverter, and when the speed requirement is less and power requirement is very high, we go for synchronous motor drive with cycloconverters. Okay. Next, continuous hot rolling mills. Earlier we saw reversing hot rolling mills. Now we will see continuous hot rolling mills. So in this continuous hot rolling mills, input is bloom, whereas output is billets or strips. And mill stands, multiple are there, some of them with roughing work, some of them with finishing work. And the mill stands come with either 2 or 4 high with different gap lengths at different stages, having a feature that progressively the gap length decreases. How the process goes on here? In the earlier case we saw only one stand, whereas here there will be multiple stands. You can see this is one stand, second stand, third stand, and whatever input we give, the bloom or the slab, that input, it is passed here, and then it is passed through this, then it is passed through this continuously. There is no reverse movement here. And you can see the gap is decreasing progressively, which means when the input is passing through different mill stands, its shape will progressively decrease, and finally when we come to the output stage, it will be of the required size. It will be of the required size. And initially these stands, initial stands will be the roughing stands, whereas the later stands will be the finishing stands. So input here is bloom or slab, and output is billet or strips. Billet or strips. Output is billet or strips. Okay. So continuous hot rolling mills will give us the billets or strips using blooms or slabs as the inputs. Blooms or slabs as the inputs. And what drives are used here? Drives are used here for rotating these rolls. Okay. Now, the requirements of these drives, the gap length of mill stand needs to be adjusted. That means this gap needs to be adjusted. Okay. And then the speed range required is large, about 1.5 to 2, and accuracy required is also more, and consecutive stands run at different speeds. That's to be kept in mind. These rolls run at different speeds, and when the continuous movement is there, in between the stands there can be sagging of metal. That is, between these stands here the metal sagging will take place. When the sagging takes place, the loop will be formed, and that complicates the process. Hence, there should be proper control of these speeds so that no sagging, that means tension at these rolls, is to be maintained properly. The accuracy required is very high and the response required is very fast. They are the requirements. With those requirements, the drives employed are DC motor drive with ward lever control along with flywheel effect, and nowadays it is thyristorized solid state DC motor drives, and that is normally referred to as solid state ward lever system. Induction motors with frequency control with inverter there is also employed. And what is to be noted here is, because there are multiple stands, those different drives, each stand is with one drive, those drives are to be coordinated. So this aspect also is to be kept in mind. Whatever drives we employ, they should be compatible to such a coordination. And DC motors are normally the motors. Of course, nowadays induction motors are also being employed here. Next, we will come to the reverse cold rolling mills. Reversing cold rolling mills. As the name itself tells, it is cold and it is reversing. It is similar to a hot rolling mill, reversing. Only difference here is it is cold. And what is the input here? Metal in the form of reel, and the output is strip, or it can be in the form of sheets. Okay, and what you can see here quickly, thin. Can you imagine the shape? Strip. Okay, so what are the drive requirements? It should be reversing type, reversal rotation. The drive should be capable of reversing because it is reversing type of application, which means it should have capability of 4-quadrant operation, and torque and speed are to be smoothly controllable with uniform acceleration and deceleration. Why? To avoid sagging, looping, breaking. If you pull very much, then the metal will break. If you don't pull properly, looping will take place. The strip tension is very important, and the diameter of the reel, as you go on storing it, winding it, the diameter changes. Along with that, this tension also is to be controlled properly, and motor inertia should be less so that it becomes fast acting. What are the drives? DC motor with Ward-Leonard control along with flywheel effect, nowadays thyristorized version, and cyclofed synchronous motors for very high capacity and low RPM applications. These are the drives employed. And we look at continuous cold rolling mills, similar to hot continuous rolling mills. Here it is cold and it works in only one direction, forward direction. There will be multiple stand gaps. There will be multiple stands with the gaps reducing progressively, and the output is wound on bobbins. And what are the drive requirements? The strip tension is to be constant. We have seen it earlier. Otherwise, it either results in breaking of the strip or in loop formation. Hence, we require speed and torque to be controlled smoothly. Even when the bobbin diameter is changing, when you go on winding on a bobbin, the diameter changes, the inertia changes, even then these should be maintained constant. And normally the DC motor used is normally the drive used is DC motor with Ward-Leonard control. And along with these main drives, there are other supporting drives employed in the steel mill. The first one is roller screw down mechanism. So what is this? I had shown here earlier this gap to be changed. To change this gap, when these rolls are very big, we need to use a motor itself. We cannot do it manually. This is gap adjustment, the drive used for gap control. Okay, so that we are referring to here, roller screw down mechanism. So here top roll position is to be adjusted after each pass, and it is required in reversing type of mills, and the drive used is thyristorized DC motor control. Okay, and next we have table rollers. I mentioned in the very first slide itself when we saw that process, the car vehicle on which you bring the ingots is carried on a car. It is taken on a bed. That bed is a roller bed, and those are to be rolled. Na? That is done by the drives, and normally either it is individual or group drive, and when they roll, the vehicle moves on that, and normally for this DC motor is employed with either line shafting or with gearing with different mechanical connections. So like that there are different additional drives. So ultimately conclusion is, in the case of steel mills, mainly the DC motors are employed. Nowadays, of course, that space is being taken by the induction motors also. The DC motor drives have the advantages that the starting torque is variable, the speed is variable, and the speed range is wide. Starting torque is high, and these motors have higher overload capability, higher pull-out torque, and fast and smooth acceleration, deceleration, and reversing possibility is there. Regenerative braking is possible. With these things, thyristorized wall-unit control is better. However, DC drive has the disadvantages. The very first disadvantage is the commutation limit. We have a voltage upper value, that is why the power rating cannot be too much and speed cannot be too much. That puts a limitation on the capacity, higher capacity. And space and weight requirement comes regarding the traditional wall-unit system. That is why nowadays thyristorized solid state approach is followed. So main demerit is this limitation on the higher power rating, maximum power rating of the motor. Whereas induction motors do not have that problem. They can be of very high capacity, and nowadays they are used with V/F control, thyristorized with DC link or cyclo, and particularly the squirrel cage variety is very sturdy, very strong, and hence it is preferred. Maintenance is very less. And coming to the synchronous motor drive, they are used typically for low speed and high power applications. They are also sturdy, and they are used with thyristorized cycloconverters. So with that, we come to the end of this steel mill application. What is very important is this first rolling of steel, changing the cross section of the metal, reducing the cross section of the metal is basically what is going on there, and it is happening with mechanical pressure. For that we use the rolls. Rolls are moved with the help of motor, drive, and the overall process is the ingots to usable shapes. This is hot, this is cold, and this is the primary operation. This is the final operation ready for application in the factories called as merchant mills. So we shall stop there. Next class we will take up the next application. Bye. Take care.